Most of the starch you eat never reaches the bacteria that matter. It is dismantled almost on contact. Consider an ordinary starch molecule, a long chain of glucose units joined by alpha-glycosidic bonds. In the small intestine, the enzyme amylase, secreted by the salivary glands and pancreas, docks onto that chain and hydrolyzes those glycosidic bonds. The chain breaks into individual glucose molecules, glucose crosses the intestinal wall into the bloodstream, and blood sugar rises. This is digestible starch, and it is the fate of nearly all the starch in bread, rice, and potatoes. Resistant starch is the fraction that escapes this digestion, and not all resistant starch resists for the same reason. Resistant starch types 1, 2, and 3 are still chemically ordinary glucose polymers. They evade amylase through physical state alone. Type 1 is starch physically trapped inside intact cell walls. Type 2 is locked in dense, semi-crystalline granules, as in green banana and raw potato. Type 3 is retrograded starch, amylose chains that recrystallize after cooking and cooling. In every case, the chemistry is native, only the geometry resists. Resistant starch type 4 is categorically different. RS4 is starch whose covalent chemistry has been deliberately altered. Each glucose unit carries 3 free hydroxyl groups at carbons 2, 3, and 6, and RS4 chemistry targets exactly those sites. In cross-linking, a phosphorylating reagent, such as sodium trimetaphosphate, bridges 2 adjacent starch chains with a phosphate diester, stitching the network together. In substitution, esterification or etherification caps the hydroxyls with pendant groups, acetyl, hydroxypropyl, or octanyl succinyl. The degree of substitution stays remarkably low, often well under 1 substituent per 100 glucose units, yet that small covalent change is decisive. The reason is mechanical. Amylase cleaves only when a glycosidic bond seats into its catalytic cleft, against a triad of 2 aspartate residues and 1 glutamate, with sub-nanometer precision. The phosphate crosslinks rigidify the chains and restrict the molecular mobility amylase depends on. The pendant ester and ether groups impose steric hindrance around the glycosidic bonds. The bond can no longer align with the catalytic triad. Human digestive enzymes evolve no capacity to work around these modifications. And where types 1 through 3 can surrender their resistance under heat and moisture, RS4's resistance is built into the molecule itself. The consequence is anatomical. Because amylase cannot grip the modified backbone, RS4 traverses the small intestine, duodenum, jejunum, and ileum, largely undigested, releasing no glucose and calling no insulin, and arrives in the large intestine, the colon, structurally intact. The colon is not empty. It houses the microbiome, trillions of anaerobic bacteria that ferment what host enzymes could not. And here, starch structure becomes destiny. Which bacterial taxa can metabolize a resistant starch depends on the exact molecule presented to them, a property called substrate selectivity. Granular RS2 and retrograded RS3 depend on a keystone degrader, Ruminococcus bromii, which physically erodes the starch granule before the wider community, species such as Eubacterium rectale, can feed. Chemically modified RS4 presents a different substrate to a different enzymatic guild. In controlled human crossover trials, RS4 selectively enriched Bifidobacterium adolescentes and Parabacteroides distisones, with bifidobacteria rising up to 10-fold in some subjects, and shifting the community at the phylum level, raising actinobacteria and Bacteroidetes while lowering Firmicutes. Same dose, different bacteria. Now follow what those bacteria produce. Fermentation yields short-chain fatty acids, acetate, propionate, and butyrate, in roughly a 60-20-20 ratio. Be precise about the division of labor here. Bifidobacterium adolescentes ferments primarily to acetate and lactate. Parabacteroides distisonis yields succinate, acetate, and propionate. Neither produces butyrate directly. Butyrate instead arrives through cross-feeding. The acetate and lactate these taxa release are taken up by butyrate-producing Firmicutes, Fecalibacterium prosnitzii, Roseburia, Eubacterium rectale, which run them, with carbohydrate, into butyrate. Resistant starch as a class is butyrogenic, though the granular types, RS2 and RS3, are the stronger primary drivers of butyrate. RS4's distinctive contribution is the consistent, targeted bifidogenic bloom that anchors that cross-feeding web. Butyrate is the consequential molecule. It is the primary fuel of the colonocytes, the epithelial cells lining the colon, supplying roughly 70% of their energy through mitochondrial beta oxidation. Beyond fuel, butyrate inhibits histone deacetylase enzymes, reprogramming gene expression, inducing regulatory T cells, the immune cells that restrain inflammation, and suppressing NF-kappa B inflammatory signaling. Butyrate also reinforces the epithelial barrier, accelerating assembly of the tight junctions, the protein seals between adjacent epithelial cells, through an AMP-activated protein kinase pathway. And in mechanistic and largely preclinical work, short-chain fatty acids signal through the free fatty acid receptors FFAR2 and FFAR3 on enteroendocrine L cells to release GLP-1 and PYY, the hormones governing satiety and glucose-dependent insulin secretion. Now the honest part, the benefits in people. The strongest, most consistent signal is acute. In controlled trials, RS4 substituted for digestible carbohydrate sharply lowered postprandial glucose and insulin responses, though part of that is simple carbohydrate displacement, fewer available carbs rather than a unique metabolic action. For chronic outcomes, the evidence is class-wide and modest. Meta-analyses of resistant starch report small but significant reductions in fasting glucose, fasting insulin, and hemoglobin A1C, with high heterogeneity between trials. Among inflammatory markers, TNF-alpha falls modestly in pooled trials. C-reactive protein and interleukin-6, notably, do not. The composite measure of insulin resistance, HOMA-IR, is inconsistent, significant in some pooled data, null in others. These are real effects, built on small, short trials. RS4 reinforces metabolic and gut function. It cures nothing, and the evidence does not support claiming otherwise. So why not simply eat for this? Because food cannot reliably deliver it. RS4 does not occur in nature, it is engineered. And dietary resistant starch is low dose and unstable. Ripening destroys RS2. A green banana loses the great majority of its resistant starch, over 80%, by the time it is fully ripe, the starch converting to sugar. Cooking gelatinizes resistant starch into digestible starch. Cooling reforms only a fraction as RS3, and reheating disorders some of that again. Typical Western intake runs 3 to 9 grams of resistant starch a day, well below the 15 to 40 gram fermentable doses used in studies. And whole foods deliver an uncontrolled mixture of resistant starch types, feeding scattered, less targeted taxa, in a dose that changes meal to meal. This is why RS4 is preferential. Cross-linked phosphorylated RS4 is over 90% dietary fiber, holds most of its resistance through normal baking temperatures, survives the small intestine reliably, and ferments in a targeted way that consistently blooms the beneficial taxa. A defined, reproducible dose that food cannot deliver. A precise substrate, a targeted result. RS4 by Fiber Labs. Fiber Labs